So we've seen that polynomial graphs all have some similarities. Domain all real numbers. They go left forever, they go right forever. They go either up or down forever, sometimes both, depending which end you're looking at. They're always continuous and smooth, but they kind of have different levels of bumpiness in the middle. And how exactly do you determine what happens at the ends, whether you go up forever or down forever? That's what we're going to talk about here. So, firstly, the most important aspect, the dominant trait of any polynomial is its degree, which is just the highest exponent you ever see on a variable. So, as we look at these four equations here, in all the cases, the highest variable exponent is 4. These are all degree 4 polynomials. What I am going to do here now is take you over to a Desmos, and I already have these all set up. If you want to follow along and graph them yourself, by all means, please do so. Or you can look at mine here. So it's the same 4 equations from the previous page. Clearly looking at them, they are not the same, right? They all have different kind of bumps and humps and dips. But what I want to focus on here is how they are similar. Specifically, our focus in this video is going to be looking at what's called end behavior. As you look at larger positive x's and larger negative x's, what does this graph do? And how similar are these when that happens? Now, when we talk about large x's, you may be wondering, what counts as large? And the answer is, it depends. Depends on the situation, depends on the context. But for us, we're probably going to be talking about hundreds or thousands. So this particular graph right now is only going to -10 and +10 for my x's. That's not very big. So what we're seeing is, right now, these graphs look pretty dissimilar. They are clearly not the same thing. But I'm going to now zoom out. Specifically, I'm going to start by adjusting just my y values. So I'm not going to move left or right yet, just up and down. And you'll notice I'm making pretty big change there. So now my y's are going from -100 up to +1,000. And already, I hope you can see that, yeah, these graphs are still different, but they're starting to look a lot more similar. Those tiny humps and dips, when you zoom out, don't show up as much. And what I'm seeing is that all of these graphs, as I go to the left, are rising, and as I go to the right, are also rising. Let's zoom out even a little bit more. Now here I'm going to change both my x's and my y's. So now my x range is going out to -100, +100. Now it's even harder to tell any of them apart. They're kind of lining up on top of each other. If I adjust my y range so that we're able to see a little bit more what's going on, at this point, I'm going to argue that these graphs are essentially the same. And the reason they're essentially the same is that when you zoom out, when you look at large x values and large y values, there's only one term that matters, and it's the term with the highest degree. The x to the 4th is running the show here. All the other stuff, it matters. It makes the graphs different, but not in an overall structurally significant way. It deals with the little humps and dips we see in the middle. But when we talk about the overall general shape, it's all determined by that highest degree term. So coming back here, I do want to summarize this. And I hope this makes a little bit of sense. For large x, the highest power has the most influence. Think about a big number, like even 100. 100 to the 4th power is 100. So is 100 million. 100 to the 3rd power is only 1 million. So this front term is 100 times larger than any of the rest of this stuff. My gosh, when we're talking about numbers this big, adding and subtracting a 3 at the end doesn't make any hardly difference at all. And that's only when x equals 100. When x equals 1,000, this front term is 1,000 times bigger. When x equals 1,000,000, this front term is 1,000,000 times bigger. And you may say to yourself, well, okay, Schrock, but what if instead of just coefficients of 2 and 1 and 4, what if we have coefficients that are bigger? I make it 200x to the third. Well, now these graphs look really different. And I agree. Let's change our window again. Let's go out a little more, out a little more. And what we're going to see is, do some window adjustments. If you zoom out far enough, you still can't tell the difference. So when you get to those large x's, it really is only that front term that determines what's going on. By far the most powerful term. Now, let's focus here on end behaviors. So what we're going to see is sometimes your graphs as you go to the right are going to go up forever. Sometimes your graphs as you go to the left are going to go up forever. Sometimes they're going to go down. Sometimes you'll have one of each. It turns out there's only two things you need to check to know what's going to happen with your polynomial's end behavior. And it is what the degree is, whether it's an even number or an odd number. And what the leading coefficient is, whether it's positive or negative. So coming back here to our Desmos, this I do want you to follow along with. So I'm going to get back to my standard zoom. And let's start off with a simple one. I'm going to pick a positive number and an even degree. So x to an even power. How about 4? There you go. What do we see? Well, I see a graph that as I go to the left is rising, and as I go to the right is also rising. Do a little experimentation here. Change the 2 to any other positive number you want. Change the 4 to any other even number you want. And you're going to see the exact same thing happening. If we make it x to the 48th power, and if I make this in front of 0.034, focusing just on end behavior. As I go left, the graph is still rising, and as I go right, the graph is still rising. Turns out that for every even degree and for every positive leading coefficient, you're going to get a graph that looks something like this, essentially a parabola. The higher your degree, the more square-shaped your parabola becomes, but the end behavior won't change. You're going to rise to the left, you're going to rise to the right. Here's what I want you to do. Do some experimentation. This is going to require you to pause and then unpause later. I want you to see what the end behaviors look like if you switch to an odd degree with a positive leading coefficient. And then do the same thing with negative leading coefficients and see how things look. So pause it here. Do your experimentation. You better have experimented and paused on your own. If I find out you didn't. What we should see is this. If you have a positive in front of an odd degree term, you're going to get something that looks kind of like this. So it will fall to the left and rise to the right. I hope that makes a little bit of sense. If I take positive x's to an even power, you get a positive number. If you then multiply by something positive, you're going to stay up. If you take a negative x to an even power, you get a positive result. Multiply by a positive, you stay up. For the odds, positive numbers to odd powers are positive. Negative numbers to odd powers are negative. That's what makes things go down there. Now think back to last semester. Remember when you multiply everything by a negative number, it just flips your graphs upside down? That's why I hope you're seeing, essentially, the reverse of what you saw up top. There you go. So if you know what your degree is, what your leading coefficient sign is, you can determine your end behavior without even needing to see a graph. So let's do just that. For each of these, I want you to do your quick pause, make your guess as to end behavior, and then unpause when you're ready to check. I want to do the first one together just so you know how I'd like you to write your answers. So first off, I simply want to make a sketch of what this looks like. So its degree is the highest exponent, so it's even degree. And the sign of the leading coefficient. Just look now at the sign of the number in front of your highest degree term. That's this one here, that's a negative. So even means my end behavior is the same. It's either both up or both down. Negative means it's going to be both down. So I'm going to describe the end behavior here as falling to the left because it goes down as I go to the left, and also falling to the right because as we go to the right, the graph also goes down. If your graph goes up, we'll describe it as rising instead of falling. All right, give this one a shot. Quick pause, unpause when you're ready to check. I see odd degree with positive leading coefficient. So that's going to look like this. So what I see is a graph that is falling to the left because it goes down to the left, but rising to the right. Okay, let's keep going. Okay, if you haven't already paused, do your pause. Degree highest exponent, and make sure you check them all because they're often in order. They're not always in order. Here's my highest variable exponent, it's even. Positive 1 as the coefficient, so it's going to be something like this. So this graph rises to the left, or rising to the left, and then also rising or rises to the right. So speaking now to those of you that are going to be doing more math in the future, I want you to understand why that's happening. Don't just memorize the chart. The chart's meant to be helpful, but understand why the chart looks the way it does. That's going to be the key to making your life easier. Okay, and now lastly, check my exponents. There's the highest one, that's odd, so my end behaviors are going to be different, one up and one down. And because this is a negative leading coefficient, it's going to look like that. Okay, so this graph rises to the left or rising, and falling or falls to the right. And that, my friends, is how you describe end behaviors.